Good afternoon, and you are welcome to uh, today's lecture. Uh, we've been having discussion on star 121, statistical inference 1, and this is the eighth in this series. So I welcome you very warmly. Today, we will be focusing on um, association, which is correlation and regression. So we will explore how variables are related. We are going to learn about methods uh, used to measure relationship, and we are going to understand how to model such relationships and use the model to predict. We are also going to be able to understand the strength of relationships uh, when the relationship is weak, when the relationship is strong, when there is no relationship at all. We will be able to quantify the relationship, and then we'll be able to uh, also predict outcomes. So let's move straight into the objectives that we set for ourselves today. One, we will understand the concepts of association, correlation, and regression. We will also be able to identify, um, differentiate rather, uh, between correlation and causation. These are concepts that are usually uh, abused or misunderstood. We will learn how to measure the strength of associations using correlation measures. Like I said earlier, you will learn when you measure the strength that will allow you to determine whether the relationship or the association is weak, is strong, is perfect, or whether there is no association at all. And we hope to uh, establish the foundation for regression analysis as a predictive tool. So we will lay the foundation uh, with a simple regression model. We will reinforce our discussion with practical examples. So these are the objectives listed for uh, today's lecture. So what is association? Whenever we refer to association, uh, we are talking about relationship between two variables. So generally, we can talk about, we normally start with two variables. So so let's say you have variable x, variable y. So for instance, x could be h and y could be blood pressure. So the we may be interested in uh, trying to know whether there is relationship between these two variables, age and blood pressure. Uh, Again, another example is advertising budget and sales revenue. So your X variable could be advertising budget. That's the amount you spend or your company spends on advertisement. And Y is the sales revenue. Uh, is there any relationship between what you spend or what your company spends on advertisement and revenue? Uh, Sometimes this is of interest to a business organization. So, do you have improvement in your revenue as you uh, spend more to advertise your product? So, association is about establishing relationship between two or more variables. So here we have looked at just two variables, but sometimes we could have more than two variables. So we can have x, y, z. So in that case, you have multi, multivariate, situation when you have more than two variables. But our discussion we focus more on the two variable situation. As so, what are the types of association uh, that exist? Uh, they are basically categorized into three. So the association could be positive, negative, and there may be no association. So for positive, if the variables are moving in the same direction, x is increasing, y is increasing, both are moving in the same direction. Or the reverse could also be the case. That is, x is decreasing and y also decreases. So if the relationship is positive, it means that the two variables are moving in the same direction. Increase in one leads to increase in the other. Decrease in one leads to decrease in the other. But it is negative if you have a situation where when x is decreasing, y is increasing, and vice versa. So here we say the relationship or the association is negative. So they move in opposite directions, not in the same direction, but in opposite directions. When you now have a situation where X and Y does not really exhibit any clear pattern, so we say there is no association, that X is unrelated to Y. So it is very important uh, in many this kind of analysis is usually very crucial in many practical applications. So identifying these relationships or patterns can be very helpful in decision making in many disciplines or fields like business, medicine, and education. So, uh, just a minute. Need to. Okay. Wow. Um, just a minute. Sorry, the slide is not moving. I need to check what is happening. Um, okay. Uh, Let me stop sharing and then share again. Sorry for that. Uh, oh, wow. I still have problem with that. Let me try to understand what is happening. Sorry. Okay, so I'm getting back. Let me share the screen again. Just a just a minute. Okay. Sorry for that. Okay, I think you should be able to see my screen now. So we will start uh, looking into the concept of correlation at this point. So we've talked about, uh, we've tried to define association. Now, uh, correlation is another concept we want to uh, establish. So correlation measures the strength. I hope you can see my screen. Are you able to see my screen? Uh, the screen is blank. Okay, I think it's coming up now. Sorry for that. Sorry for that. Yeah. So, are you able to see the screen now? Great. So, we are trying to now define correlation. And earlier we talked about association, which is simply to establish whether the association is positive, whether variables are moving in the same direction, or whether they are moving in opposite directions, or whether there is whether the variables are not related. But correlation now helps to really measure. So correlation analysis helps to quantify that relationship. So not just to say they are positive, but also to say in a numerical, in a measure, in a metric form, what what that level of correlation is. So correlation analysis measures the strength and also the direction of a linear relationship between two variables. So underline those two terms, the strength, let me change the color, the strength, the direction, and no, most importantly, the measure. So it's a statistical measure, and that measure will indicate the strength and the direction. But what type of relationship are we interested in? Linear relationship. So it is very important to know that correlation is about linear relationship. So if you have y, you have x. Um, relationship may not always be linear. So relationship like this one is not linear. Relationship like this one is also not linear. So there could be non-linear relationships, but correlation analysis focuses on linear relationship uh, between two variables. So this is the formula for measuring the relationship. So which means for us to measure the relationship, we need to compute these expressions. Uh, we will see the step by step later for computing these expressions. So when you compute the R, which is the correlation coefficient, we call it the correlation coefficient. It was actually developed by Pearson, so we call it uh, Pearson correlation coefficient. So the value of the coefficient will always lie between two intervals, -1 and +1. Of course, there is 0 here. So R is a number between -1 and +1. It cannot be less than -1, and it cannot exceed +1. It can't be greater than +1. So it's a value that can take, is a measure that can take values between -1 and +1. And you know, in that range, 0 is there. So which means correlation coefficient can as well be 0. And when it is 0, it means there is no linear relationship. So when it is on this side, between 0 and +1, then we say there is a positive linear relationship, which means the two variables are moving in the same direction. When R takes value that is in this area between 0 and -1, between -1 and 0, then we say there is a negative linear relationship, which means that the two variables are actually moving in opposite directions. But when R is 0, they know that there is no linear relationship. And so the values can be very close to 0. It's very rare in practice that the value will be exactly -1, but it could be very close to -1. So if it's close to -1, then we say the strength is very strong. So when it is close to 1, we say it is very strong. So values like, any value exceeding 0.7 may be considered, but this is not fixed. But generally, this can be it can be taken that any value above 0.7 is a strong positive linear correlation. Similarly, any value that is below -0.7 is a strong negative linear correlation. But if the value is hovering around 0, like 0.1, 0.2, or below 0.3 or so, then you know that there is correlation, but it's very weak, not so strong. So you will notice that when you measure the correlation, one, it gives you sign. It also gives you metric. The sign shows the nature of the relationship. So positive, negative. The metrics shows the strength of the relationship. So that is the beauty of correlation. So correlation helps you, one, to know the direction, and also to know the metric, the strength of the relationship. So that takes us to uh, look at an example, to further uh, drive home this discussion. So we have a scenario here in which we want to study, or want to look at or examine what type of relationship exists between hours of study and performance, measured in terms of exam scores. So, uh, is it um, what kind of relationship? Uh, is it that as you spend more hours studying, then you are likely to uh, perform well, or the better your performance? So, in other words, does the two move in the same direction, or do they move in opposite directions? So, to answer that, concern, to establish that relationship, uh, 10 students were observed. The researcher studied their study, for each of them, the hours spent studying before the exam, and also the exam scores. So the first student spent 2 hours studying and scored 50. So that's that. The second one spent 4 hours studying and scored 55. The 10th one spent 20 hours. No, I think he or she slept just for 4 hours, and then scored 95 in the exam. Maybe some of you are like that. So, what is the relationship, between, or what kind of relationship exists between study hours and exam scores? So to do that, we have to calculate the Pearson's correlation coefficient. So to do that, we need to look at the step by step for doing that. So the first step, you may create a table. These days, of course, uh, if you know software, Excel can easily do that for you. So you can have a table where you have X and you have X minus X bar, and then you have another one here, X minus X bar squared for this one. And then you also have y minus y bar. You also have y minus y bar squared. So, uh, for instance, this is 2, this is 4. So the first thing is to obtain the mean of x. So you can find the mean of x bar, and then you can find the mean of y bar if you sum that. And then uh, the mean of the X bar is the mean of the study hours, and the Y bar is the mean of the exam score. And once you get that, you can get this column, which means 2 minus the mean, 4 minus the mean, and so on and so forth. And of course, what you have here is the square of whatever you have. What you have here, as I said earlier, will be 2 minus the mean, 4 minus the mean, 6 minus the mean, and then here you square whatever you have here, you square it here. So that gives you uh, that the values in this column. And then here you can now sum it to get the sum of xi minus x bar. That will be the value here. Then when you do the summation for this, that will give you the value here. Sorry, when you do the summation for this, that will give you the value here. When you sum the one here, that will give you this one. And when you sum the one here, that will give you this expression. So, uh, so this after the step one of uh, getting the mean of each variable, mean of study hours, mean of exam score, then you get the deviation from the mean. So that gives you the deviation of study hours. That is this column. And then the second one gives you the deviation of the exam score. That again you get. And then of course you get the uh, product and the squares of deviations. I've shown you how to do that. The product is the numerator, the product of the deviations. And then, uh, so the product, the product, you can also get it by having another table which will be x minus x bar and then y into y bar, which means you multiply the value in this column with the values in the corresponding cell here. So you get that, and you get the square of the product of the deviations, and then you get the squares. So that's the value here. And then the final thing is to sum. So the summation will come at the end of the table, and then you substitute and you get the values. So going by our example, the mean study hour is 11. The mean exam score is 75. And then the sum of product of deviations is 910.0. The sum of square deviations for study hours is 330.0. The sum of square deviation for exam scores is 2510.0. And when we substitute that, that is this value, and then the square root of the product of the sum of square deviations, the product, that is 330 and 250, the square root. And that gives you approximately 0.975. First of all, you will notice that the sign is positive, so which means the relationship is positive, and that implies that uh, they move in the same direction. So study hours and exam scores move in the same direction. So if a student spends more hours studying, the student will perform uh, the performance will also improves. So that is what the data has shown. Uh, that's what is coming from the data. Another set of data might show otherwise. But you are analyzing based on what the information your data is providing. So one, we know the sign is positive, and then the magnitude, which is 0.975, that measures the strength. And since that value is very close to 1, which is the highest it can take on the positive direction, so which means it is a very strong positive linear relationship. So we can conclude based on this that uh, there is a very strong positive linear relationship between study hours and exam scores. So you can also maybe you can collect your own data. You take I don't know how many courses you are taking. Just uh, take record of the hours you spend uh, studying each course, and also look at your performance in the course. Take the data and analyze yourself and see what kind of uh, inference you can draw. Whether you as a person, your performance is what you get high score, or when you study uh, for longer hours. Uh, so the situation might differ from person to person. So you can study yourself. Now that takes us to one critical uh, issue, uh, and that is correlation versus causation. Correlation is actually talking about you have X, you have Y. Just maybe, let's say, just these two variables. So it's about, is there a relationship? Is there an association between the two? It's not saying that one is causing the other. It is not, you notice that we have not talked about whether uh, X is causing Y or Y is causing X. We are only saying there is association, there is a relationship. So in causation, you may have X causing Y. So in that case, correlation does not imply causation. So when you analyze, as we have just done, that there is a relationship, it does not imply that one is causing the other. It only implies that there is a relationship. There is an association. So, and there are many situations in life that there may be association. An association can even come by chance. You may, for instance, sales of ice cream and the event of drowning, people getting drawn. Uh, these are likely going to just, there might be, you know, uh, superficial kind of relationship, because the two will possibly call during wet season, rainy season, or you might have low sales uh, in wet season and low incident or high incident of uh, uh, drowning incidents during the wet season. And if you conclude that, okay, it would be wrong to conclude that uh, high sales of or low sales of ice cream is responsible for low uh, drowning incident or vice versa. So there may be that kind of superficial relationship which one cannot really, it doesn't show that one is causing the other. Look at another example of shoe size and math, no, uh, math skills. So the fact that one is good, so shoe size and math skill having correlation because of age differences, you know, not because shoe size affect math skills, you know. So the point, the takeaway here is that it must you must always learn to investigate the underlying factor, before you can determine causation. You need to do more rigorous analysis before you can establish that X is causing Y or vice versa. But at this point, our concern is about correlation. But don't extend beyond, you know, uh, establishing relationship to now claiming causation. Don't go to that point. Simply, when you are interested in correlation, simply look at relationship or no relationship. If there is relationship, then what type of relationship, positive or negative. But don't go to say one is causing the other and vice versa. So take note of that. You need to do more to establish whether X is causing Y, whether performance in physics is as a result of the performance in mathematics. Uh, so you need to go for that. But there could be relationship between performance in physics and performance in mathematics. Uh, and you can use correlation to establish that. But beyond that, you need to do further analysis to know which one is causing the other. So the causation might be this type, where X is causing Y. You can also have a situation where uh, uh, you have uh, bidirectional, so X causes Y and Y also causes X. But we are not going to discuss about causation for now. But the one we will discuss, we are not discussing this, but we will now look at this one. And that takes us to the uh, regression analysis. That takes us to regression analysis. So in regression analysis, we now try to use the knowledge. So first, we have, uh, in regression analysis, you may have two variables, x, y. So, uh, so we may want to model, the relationship between x and y. So uh, the x is usually the variable that is considered to be explaining y. So if x is the variable that is explaining y or that is influencing y, then we will say y is dependent. So we will say y is dependent. If x is the variable that is explaining y, then x will be called the independent variable. So, which means the variables in regression are usually categorized into two: dependent and independent. So, the dependent variable is the one that is being explained. The independent variable is the one that is explaining, so we call it explanatory variable. At times we also call it the regressor. So, but for now, just know that the variable, that is being explained is the dependent variable. The variable that is explaining it is the independent variable. So in most situations, you will always have one dependent variable, only one, but you may have one or more independent variables. So in regression analysis, so you will have one dependent variable and one or more independent variables. So when the number of independent variables is 1, then we say we are dealing with simple linear regression. So in that case, you have the dependent variable y. You say you are regressing it on independent variable x. So this is, in simple regression, you have one dependent y and one independent x. But if you have y on x1, x2, x3, that means you have 3 independent variables. So in that case, you you have multiple linear regression. So what differentiates simple from multiple is the number of independent variables in your regression model. So we will only discuss this one for now. So that's because there are only 2 variables there. So we also call it a 2-variable regression model. So simple linear regression is also known as a 2-variable regression model, and it explains the relationship between one dependent variable y, so you have dependent, and one independent variable x. So this is the equation. This is the equation. Y equals beta naught plus beta 1 x plus the epsilon. That's error. So we'll look at what each of them represent. So the beta naught here, just a linear equation generally you have for y equals to mx plus c. So this expression is from a linear equation. So if you are already familiar with that. So beta naught is the constant, is the intercept. That's where the line, cuts the x-axis. And then the beta 1 is measuring the slope of the, so it's measuring the slope. Measures the slope. This is the slope. So this is your beta naught. or rather beta 1, and this is your beta naught. So that's beta naught is the intercept. Beta 1 is the slope, which is a measure of the change in y for a unit change in x. The epsilon there is the error term. For now, we are not going to talk much about that. So, uh, uh, so in subsequent uh, classes, in statistics, you will learn more about that error term, the assumptions, and all of that. So, the formula is reproduced here. So we have uh, the equation which expresses the dependent variable y as a function of independent variable x. So the y is the dependent variable, which is also called the response variable. That's the variable we are explaining. The x is the independent variable and is also called the predictor variable. If you look at this very well, so we will need data for y, we will need data for x. So, but beta naught and beta 1 are values that we don't know. And so we have to estimate them from the data we have on x and y. So they are called constants, the unknown constants. They are unknown constants. But we will see the formula for calculating them very shortly. But in terms of what the role they play, for instance, if we just for now ignore the error term and then we put beta 1 to be, we put x to be 0, which means beta naught, so I will have y to be beta naught plus beta 1, 0. And this will be 0. So which means y equals to beta naught is the intercept, and it simply gives the value of the dependent variable y when the independent variable is 0. So the beta 1 measures the slope, so it tells how much y changes for every unit change in x. That's the measure of the slope. So the error term accounts for the uncertainty, the variability in y. That is the part of y that the model cannot explain. So if you look at the model, the part here represent the part that the part of y that can be explained, and the error term represent the part of y that cannot be explained by x or by the model. So how do we now calculate? So if we, as I said earlier, with the true values of beta naught and beta 1 are not known. So we have to estimate them using sample data. We have to draw sample from the population. So that gives you an estimated regression equation. So whatever we get from the sample for beta naught, we will now call it B naught because it's coming from the sample. Whatever we get for beta 1, we will call it B1 because it's an estimated slope. Whatever we get for beta naught, we call it the estimated intercept because it's coming from the sample. And then we use cap to indicate the predicted value of y. That is why the predicted value may not give you exact, the actual value. So the difference between the predicted and the observed, the actual, is the error term that we are talking about. But again, we are not going in that direction. So how do we calculate the value for the slope, B1? And how do we calculate the value for the intercept, B naught? So you will always need to calculate B1 first before you calculate B naught, because you need the value of B1 in the formula for B naught. You are already familiar with this. This is the sum of the cross product of the deviations of from the mean of x and deviation from the mean of y. The sum of the cross product is what you see in the numerator. The square, the sum of the square of the deviation from the mean for x is what you see in the denominator. So try to compare this formula with the formula for the correlation coefficient. The numerator are the same, but the denominator, they are different. So, and once you get your B1, you can substitute here. You only need to get the mean for the dependent and then subtract it from the product of the slope, estimated slope, and the mean of the independent. That gives you the beta naught. So we can look at data, look at this simple data, which is about house prices and the size in square feet. So it's relating house prices with the size in square feet of the house. So this first one, there are 5 observations here. So this first one, for instance, the size is 800 square feet, and the price in dollar is 200. Remember, it's in thousands. So for this 1,000 square feet, the price is 250, and then 1,200, the price is this. So the model we are trying to fit is to see whether the price of the price, how the price can be used to um, uh, how to predict the price based on the size of the of the house in square feet. So the the price in this case, the price is uh, y, and then the size is x. So in other words, uh, we are y, so we are fitting price, that is y equals to a plus b, and then multiply x, in our case is the size. So in other words, give me the size. If I know A and B, then I can predict the price of the house. So if we now compute the B, in this case, the B, we use this formula to compute the B. You can do that. Then the value will be 0.2. That is the slope coefficient. And if you compute the A, which is the intercept, it is 50. And that is now substituted in the model. So which means the price, which is y, is equals to 50 plus 0.2x. So which means this 50 represents the price of the house when the size of the house is 0. So but the question is, suppose you want to predict the price of the house for a house of 2,000 square feet. So in that case, we are given the value of x. So that's how we will now substitute. So we have 50 plus 0.2 times 2000, and that gives us 450, which means the predicted house price for a 2,000 square feet house is $450,000. So this is how regression is calculated. Before we close the discussion, it's very important for us to consider the relationship between correlation and regression. The one, correlation, as earlier mentioned, measures the strength of the relationship. So not only the strength, it also measures, it gives you the direction. So positive or negative, and how much positive or how much negative. So it's not talking about prediction. Regression will also help you to quantify relationship by predicting the dependent from the independent. So high correlation implies a good fit for regression because um, if the relationship is very strong, then the tendency is that you can use one to predict the other, which means if the relationship can help, a high correlation can help to improve the predictive performance of regression model. But always also remember that you know, correlation does not imply causation. It doesn't imply that X is causing Y or Y is causing X. So here you have another expression that you can use to compute the regression coefficient. So if you get the correlation, then you can multiply it with the ratio of the standard deviations of X and Y. That will also give you the coefficient. So in essence, you can see how correlation is related here, how correlation is related to the regression coefficient. That's the point we are trying to make here. So, how can we apply this discussion? Which fields? So, in economics, well, you must have heard about economists predicting the gross domestic product. That occasionally IMF will say Nigeria economy will grow. We predict that Nigeria economy will grow by 3%, 2%, 5%. So regression is used in economics to predict growth. In medicine, you also uh, study risk factors for disease, relationships. You will see whether smoking is related with age, or whether um, uh, uh, smoking is related with uh, gender. So there are so many uh, risk factors that you want to in medicine that are usually of interest. In marketing, you study, you know, uh, ad, advert effectiveness, whether advertising on radio, you know, the cost of advertising on radio is related to marketing revenue, and so on and do that. In education, correlation and regression is also very, very important uh, to understand factors that influence student performance. So both correlation and regression are indispensable tools across disciplines in engineering, in botany, microbiology, social sciences, even in arts. So uh, correlation and regression, they are widely used. So let's summarize this lecture and then move to the usual post-lecture quiz. The takeaways for this lecture, one is that uh, in association, our interest is to establish relationships between variables, positive, negative, no correlation. Are they moving in the same direction? Are they moving in opposite direction? The next level is correlation, and that helps us to measure the strength and the direction of linear relationship. I emphasize that, not just any relationship, but linear relationship. And then, so once correlation is identified, then we can use regression uh, to predict. You can use regression uh, to predict the dependent variable. So regression predicts uh, dependent variables based on the independent variables. So in regression, you need to know which variable is dependent, which variable is independent. And we said we could have simple regression and multiple uh, regression. Simple, you have one dependent, one independent. Multiple, you have one dependent and you have uh, two or more independent variables. So both correlation and regression, uh, they are essential for exploring and quantifying associations. So don't always jump to conclude about causation without seriously investigating the underlying drivers. Always check assumptions We've not talked about assumptions, but maybe in subsequent courses you will take in statistics, we will talk about assumptions before. So I advise you to practice with data, though, and you can also use statistical softwares like R, Excel to analyze, correlation and regression. So this is the end of the lecture, but before we go, we are going to review, evaluate what we have learned as usual. So the first question, are you ready? Let me see. Yeah, are you ready? Please, how did you calculate the intercept and the slope? Yes, I showed you the formula for the intercept. Uh, so uh, then, yes. So the first question, what is the range of the Pearson correlation coefficient? Yeah, okay. What is the range of the Pearson correlation coefficient? Yeah, uh, the consensus seem to be B, and that looks good. So the Pearson correlation coefficient ranges from -1 to 1. So you are correct for those who have chosen B. B is correct. So it indicates the strength and direction of the linear relationship. Question 2. Which of the following indicates a strong negative correlation? Which of the following, question 2, which of the following indicates a strong negative correlation? Nobody has responded to yet. Question 2. Which of the following indicates a strong negative correlation? A strong negative. Teslimot and Joy. Check your answer very well. Teslimot is saying C. Joy is also saying C. Strong, -0.1 is very close to 0. So since we are talking about negative, we are talking about, I showed you, if you have here, you have -1 and you have 0 here and you have +1 here. We are talking of strong negative correlation. So you will be expecting something that is here to be, because it's negative, so here you have negative. You can't even talk about this side at all. So on this side, anything close to -1 will be strong. But if you are choosing value close to 0, that is weak. No. So this is strong positive. This is strong negative, which is what we want, but we don't want this. This is negative but weak, and r equals to 0, no correlation at all. So the correct answer in this case is uh, is uh, is B. I hope that is clear. Uh, let's look at yes. So the correct answer is B. Question 3. Uh, in the regression equation, y equals to beta naught plus beta 1x. What does beta 1 represent? What does beta 1 represent? What does it represent? The intercept of the line, the slope of the line, the predicted value of y, the error term. Everybody should get this, I suppose. Everybody should get this. Yeah, everybody should get this. Okay, your responses look great. So you are correct. Your correct answer is B. Correct answer is B. So beta 1 is the slope representing the change in y for a unit change or no, a unit change in x. Question 4. If r equals 0, that's the Pearson correlation coefficient. If is equals to 0, and uh, I've just explained something like that now. What can be inferred about the relationship between the two variables? A, they are positively correlated. B, they are negatively correlated. C, there is no linear relationship. D, they are uh, causally related. They are causally related. Uh, who is Sakit P. Timothy? Okay. Timothy, you might need to check your answer very well. Uh, Timothy, you might need to check your answer very well. Interesting. So, the correct answer, let's see, is actually C. So, when the Pearson correlation equals 0, it means there is no linear relationship between the variables. So, though uh, they may have a non-linear relationship, and I mentioned that there may be non-linear relationship, but this Pearson correlation measures linear relationships only. Question 5. What is the primary purpose of regression analysis? As we discussed, what is the primary purpose of regression analysis? Question 5. Nobody has responded to question 5. What is the primary purpose of regression analysis? To measure the strength of association between two variables, to predict the value of dependent variable based on independent variable, to identify causation between variables, to test for normality in data set. Most likely, a lot of you will already know. Majority are choosing A, and I don't know why you are choosing A. So the correct answer for 5 is B. I think I emphasized that, so much. Regression analysis models the relationship between variables, so that you want to predict the dependent variable based on one or more independent variables. So regression is for prediction, you know, correlation is for uh, measuring association, measuring relationship. Okay, so question 6. Which of the following is not a key assumption of simple linear regression? This may be technical. We didn't discuss this much, but I expect that you should know. The key assumption actually is that there is a linear relationship between x and y. It is assumed, that x and y, or the two variables, are linearly related. And I think I mentioned that. So it's a fundamental assumption. Uh, I don't know what your choices are, but for 6, the correct answer is A. People have not responded to 6. I can still see most people responding to, yeah, most people okay. Yeah. So for 6, the correct answer is which of the following is not a key assumption? Okay. Yeah. The correct answer is D. Sorry. Uh, uh, the correct answer in this case is D. These are correct assumptions, though we didn't discuss them, but this is not a key assumption. There is no emphasis on what the correlation measure should be, for you to run linear regression. So let's move to 7. We are going to 10. We are almost done. In the context of correlation, which of the following statements is true? In the context of correlation, which of the following statements is true? Correlation implies causation. Correlation measures nonlinear relationships. Correlation quantifies the strength and direction of a linear relationship. Correlation is always positive. Everybody should get this. Question 7. Yes, I can see Abraham, Miriam, Olamilekan, Uraola, Taoka. That's good. So, Sheriff Dean, Makinde, that's good. Okay, I'm glad that the correct answer is C. Correlation measures the strength and direction of a linear relationship, but does not imply causation. Question 8, the equation y equals to 50 plus 5x. 50 is beta naught, or the intercept, 5 is the coefficient. No. What is the predicted value of y when x is 10? So if you are giving x to be 10, what will be y? So A 50, B 55, C 100, D 150. Everybody should get this. You don't even need a calculator. Question 8. Great, great, great. So if you are given the intercept and you are given the coefficient, the slope, then you can always calculate the you can always calculate the Okay, so let's go to the next question. So the correct answer for that uh, is actually 100. This is now question 9. What does a correlation coefficient of R equals minus 0.75 imply? What does a correlation coefficient of R equals minus 0.75 imply? A, a weak negative linear relationship, a strong negative linear relationship, a strong positive linear relationship, no linear relationship. So we can even first of all rule out this. We can rule out this because and is positive, not negative. Then we are left with 2. Is it weak? No. Is it strong? This is very close to minus 1. So the correct answer in this case is B, a strong negative linear relationship. Finally, question 10. Which of the following is an example of spurious correlation? No, that's spurious correlation. Which of the following is an example of spurious correlation? Advertising budget and sales revenue. We expect that maybe there will be a relationship. Ice cream sales and drowning incident, education level and income, study hours and test scores. What do you, question 10? Yeah, I think we mentioned this. So some correlations that are spurious are those correlations that just uh, shows relationship just by chance, not that there is any underlying factor. So the correct answer is B. So ice cream sales and drowning incidents are correlated maybe due to seasonality, not that one is causing the other. We mentioned that in our discussion. So this is how far we go in this lecture, and of course in this course. So this is uh, the end of the lecture series for statistical inference 1. Thank you very much. Thank you. Except there are questions, let me know. So regarding the test, the announcement will be made on the WhatsApp group. So make sure you monitor the, look forward to that. Hopefully before the end of this week, let's say tomorrow, you'll get the announcement. So thank you very much. I wish you the best in your exams. Bye.